Okay. Before I get started on the problem of the day, I'm hoping that I wanted to do the discuss the backtracking contest and have us start looking at this thing. There were a total of 10 programs submitted to the backtracking contest. And the TAs diligently ran all of them on a large number of examples. And most people were able to do 8 vertices just fine. But when by the time they had gotten up to grid graphs and so basically the vision was we would try different graphs, and as he would a larger program, he would allow a minute, okay, and then when if he couldn't get the program to get the answer, that person would be struck from the competition. There was a battle, there was a battle on the grid graphs. There were about 4 programs that could handle the grid graph of size, the binary tree of size 20. Actually, more than that. But when we got to a grid graph of size, size 30, only about 4 of those programs could deal with it. By the time we got to the grid graph of size 33, okay, another program went out on with 175 seconds. But some of the others were not sweating at all. They were still taking fractions of a second. The one that proved to be the hardest for people seemed to be grid graph 3660, and that knocked out all but as far as I can tell, 1 competitor. Okay, and that competitor was Ronnie Chen. He did it in 2.9 seconds. And was able to go work up to a lot of other bigger graphs that some of the others failed. So the 3 programs that came in first, second, and third were Ronnie Chen, Daiwen Liu came in second, and Cassie Hu came in third. Are any of the people on the call? If any of you are on the call, I would like you to speak up. Is there Ronnie Chen on the call? Is there Daiwen Liu on the call?
Yes.
Yes, okay, good. And Cassie Hu, are you there? Okay, we've got one. Okay, Daiwen Liu. Okay, tell us about your program. I want to now know what did you do for your pruning?
So for the proving, hold on, let me grab my I forgot my thinking process, sorry.
Right, okay, so remember it was the bandwidth problem. We were trying to take a basically presumably build up a solution, okay, where you're trying to come up with a permutation of the vertices. My solution vector A was going to be a permutation of the n vertices. And what we wanted to do was to minimize the length of the longest edge. These vertices it's going to be in order of the vertices, and we wanted to minimize the length of the longest edge. And I wanted to talk about how the good programs work for pruning. Okay, how did you do your pruning? What did you do?
So for the proving, I get on a candidate, and I check whether there's a the vertex that's before the maximum length, and there's a edge exists between them. So if there's a edge between them, then I will just throw away the whole candidate list and just get to the previous recursion state and get to the next new.
So let's think what this means. So one possibility is we took a look at the previous the part of the permutation we've already put down, and we count and we say what is the length of the longest edge, okay, from here to between two vertices in there. And if the length of that longest edge is as big or bigger than the best solution we have, we should immediately backtrack. Is that what you did?
Yes, yes. I would just throw away the whole candidate list and go back to the previous state and just iterate again.
Okay, now my question is, did you prune only on the edges within the region that you would put down?
Sorry,
or was there a more powerful pruning criteria?
Can you ask your question again? I didn't quite
No,
get it.
if I'm trying to judge how good this partial permutation is, one way to do it would be measure the length of edges between two vertices that are already specified, right? Here there is an edge from 5 to 3. Therefore, this solution can have has a cost of at least 1, 2, 3, 4. Backtrack based on the 4. Is that what you did?
Yeah, kind of.
What other, is there any other pruning thing that you could have done?
Is there any other? Oh, let me see. I think I got 2 proving. Sorry, I'm really bad explanation.
Okay, let's look at some other ideas. Does anybody have any other ideas that we could use to judge what the potential of this permutation is? Okay, any ideas? My question has to do with, what if we look at point number 5 here? And suppose 5, we agree 5 has an edge to 3. What if 5 has 2 more vertices that have not yet been put down? Okay, that are that we are going to have to put down. 5 has 2 neighbors that are not among the vertices 6, 7, 8, 3. Is the best we can do? Is it that this is the best that we know that this thing, any extension has to have a bandwidth of 4? Or do we have a higher upper bound on this thing? Do you see what I'm saying here? You put these things down. For every one of these vertices, some of their neighbors are going to be in the partial solution, and some of them are not. What do we know about the minimum bandwidth of any way to extend this if vertex 5 has 2 vertices that are not yet in the partial solution? What do we know? Okay. Does anybody see this, preferably with a voice?
It would have to be greater than.
I am claiming that if we know that we've got 2 other vertices that are neighbors of 5 we haven't yet put in the best of all possible worlds, the further of those neighbors will be put here. Does everybody see that if this is K that we put down? In this case, the best possible solution would not be 4, but would be 4 plus 2. Does everybody kind of see that? And this is true for every vertex here. If we know what the degree of these vertices are, okay, and whether they have been, how many of their neighbors have not been used, okay, I claim we can get a better lower bound on what this solution can possibly do, okay? How many people are understanding this? I feel like I'm speaking into the wilderness now. Do people kind of see what this pruning criteria is?
Makes sense.
Okay. So this would potentially let you get much further along than what you are doing. Okay. Does everybody kind of see that? Okay, Cassie, were there any, I see you're now on here, you finished third. Are there any, what you call it, pruning ideas that you used? Going once, not hearing anything.
I started with the vertex with the lowest degree.
So one possibility is you're saying you start with the vertex with the lowest degree. What I think what you're telling me here is that you are, again, in construct candidates, all the vertices, the order of the vertices is something we have control over, right? And your hope is to start with vertices of low degree. Why did you want a vertex of low degree? The hope is that a low degree one won't have a big, what you call it? What if you have a low degree one, you won't have a, what you call it? It would be probably better to have a low degree vertex if you want to get a small bandwidth. I think that's what you're kind of thinking about. Okay. My feeling is you get a choice here. I might like the highest degree vertices first, because I could use this trick to prune. Does everybody see the high degree vertices? Give me the opportunity to prune quicker. Okay. And maybe, it should be clear I have the opportunity to order the vertices. And by ordering the vertices, I can potentially get quicker cutoffs here. Any other ideas people used in pruning or anything like that? And if Ronnie's Chen is here, I encourage them to speak up. Okay. Any other questions? The question of what would I use as my data structure here? Well, it probably doesn't matter as much as the pruning thing, but I would say that almost all the graphs I gave you were sparse. I would almost certainly use an edge list, okay, where I'm representing it perhaps as a list of edges or an adjacency list, okay, because most of the graphs I give you are pretty sparse. So that would have been probably how I would have represented the graph. Any other ideas of how you might have pruned this thing? Okay.
So if you're generating a solution right now and your current minimum, so you calculate the minimum each step. And if your current minimum is greater than your global minimum, then just throw it away because there's no way you can get a smaller minimum.
Okay, so what I think what you're telling me is, before I even did my backtracking thing, you may have run a heuristic to get a pretty good solution. Okay. And the hope would be that if you did a pretty good solution, okay, if you said, look, if you happen to find a solution of the right size, the purpose of the backtracking is to eliminate the possibility of getting better. Okay. So I do suspect that the best programs didn't start from scratch, but started from a heuristic solution. And again, generally, what are we going to want to do? So long as the longest edge we have constructed, the minimum backtrack for this thing, if it isn't going to be better than the best one we have, we immediately backtrack. Okay, that I think is an important thing. Any other ideas here? Okay, and again, I'm not being able to read this, or any other questions about this? Okay. The program that that was the winner seems to have been able to do, again, did grid graphs, 36 vertex grid graphs in 3 seconds, and seems to have done pretty good on a lot of other graphs. So it's probably a decent program. Any question about that? Okay. I don't know for sure if it did as well on the random graphs or not. This one on the random graphs certainly had no problems dealing with random graphs of size 20 vertices, but I'm not sure if it did better than, on bigger ones. Any questions? So, okay, so I want to congratulate our three winners. Okay, Ronnie Jen was first, Daiwen Lu was second, and Cassie Hu was third. I want you guys, I give as a prize something priceless, namely the gift of one of my books. So I want, but of course, this is a COVID time. So I want you guys to figure out a way for me to get this book to you, and I will do that. Normally, I bring them to class and sign them. I can't do that this year, but I would like to get you your prizes. Any questions?
Okay, thank you.
Okay, and we'll give a round of applause to our winners. Okay, as far as the worst program, the worst submitted program seems to have what you call it, seem to have died on the second test. But no. I would say that people probably could probably get up to 8 or 9, 8 to 10 vertices by doing all permutations exhaustively and little pruning. Okay, but in order to get up to the much bigger graphs, you needed to do something smarter. Any questions? Okay, any other questions about backtracking? Okay. The question of, can you use a whiteboard instead of your scrap paper? I'm going to say no, use scrap paper. Okay. I don't trust people with whiteboards in their home. Okay. I'm just not used to it. Let's just say everybody uses scratch paper. Okay. Any question? One sheet of scratch paper, blank on both sides. Any questions? Okay. The next thing I'd like to talk about quickly is the problem of the day, okay, which is getting back to dynamic programming. It has to do with dialing a phone in an efficient way. You have a phone number you want to dial, 2, 3, 5, 7, 6. 8, 6, 9. Okay. You have a phone. Again, actually, I grew up thinking of phones as differently than you. I think of a phone as having a keypad like this. Okay. And on my keypad, the digits are arranged 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And then I have a 0, and it looks like I have a pound and a star. And if I wanted to dial a phone number, if I have one finger, this is not very complicated. Okay, I could then I move my finger to the first number, and then I move push the button, then move it to the second number, then move it to the 5th number. So it's easy to dial a phone number efficiently if you only have one finger. But fortunately, we have 2 hands, okay? And if we wanted to dial a phone number more efficiently, maybe we can assume that there's a speed at which you move your hands, okay? But my claim would be that you would want a position, okay, to optimally press the phone. You might want to position your fingers, spread them out in some way, or cluster around things based on what digits you have to dial. If the phone number you're dialing is 2, if the phone number you're dialing is 29922229992, then obviously you would be best off positioning your fingers at 2 and 9 and then going blip, 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 blip. Okay? The question is, in a world for any number, could we find the most efficient way to deal with it? Where what we're trying to do is to minimize the amount of movement around the keyboard that our fingers do. Okay? So we are given this keypad. We're given that our finger F1 started here. Our finger F2 started here. We have a phone number we want to dial. Can we figure out the cheapest way in terms of finger movement to do our dialing? Okay, any questions about that? What the destination is, what the goal is?
I have a quick
Okay.
small question.
What would question? I can't hear you. What was that?
Oh, can you hear me now?
Yes.
K equals 16. On the keypad you drew, I see 12 keys. So
Okay,
why would
that's
K be
because your
16?
vision isn't so good. It really said K equals 12.
Okay.
Okay. Any question about that? Okay. So what is the right way to do this? How do you do this kind of thing as a dynamic programming problem? To me, this smells like a dynamic programming problem because we've got, we've got a sequence of things. Sequences are ordered. We've got kind of a state of things. I've got 2 fingers. There's only 12 fingers on the keypad. My claim is that there's only a finite number of places my fingers can be at any one time. And if I think about what I want to do, what is the function I want to define? I am going to claim the function that I want to define is something like this. C sub, let's call it K1. Well, let's say F1, F2, I, which is equal to the cheapest way to dial the first I numbers, first I digits, where finger F1, where left finger ends on key 1, on F1, and right finger ends on F2. Does everybody see that if I knew this function, knew what the answer was, I would know the cheapest way to dial the number, because I'm going to ultimately be interested in what is the cheapest way to dial the number. I'm ultimately going to be interested in, I claim, the min of C, F1, F2, N as F1 and F2 are both between 1 and 12. We agree that there's 12 places I can put my first finger. There's 12 places I could put my second finger. I want to now know ultimately what is the cheapest way to dial the whole number. Okay? And I don't care where my fingers are. If my fingers end up like this, but I've dialed, and that was the fastest way to dial the number, I'm perfectly happy. Okay? Everybody kind of see that? So if that is true, what is the cost of dialing the first I digits ending up at F1 and F2? What is the cheapest way of doing that? Can anyone start to sketch what a recurrence like this might be?
I have an idea. I said it would be the minimum of 2 different terms.
Minimum of what?
The minimum of C of notation is kind of funny, but like F of I, F sub I. So it would be a term for the left finger and a term for the right finger.
Okay, so you're gonna have let's
It'd be
call
like
it L, so L and R to be positions of your finger. Okay, what's the third argument?
I plus 1.
Plus 1
Well, I guess you're counting backwards, huh?
Minus one.
I'm
You're
minus
counting
one,
on
yeah.
a prefix, right?
Mm-hmm. And
Right.
then that plus the distance between, and if this was the term for, like if we chose the left finger, it would be the distance between the left finger and I guess, or yeah, I think.
And I,
It would be whatever, yeah, or
okay. So what do we want to deal with it? I want to claim that this is the cost of the previous state you're trying to get at,
right.
is my fingers used to be on positions L and R after I had dialed the first I-1 digits. Now I'm going to pay a cost that is the distance of moving the left finger from L to F1
Yeah.
and the right finger to F2. Okay. I mean, if the key thing, I guess, is I'm allowed to move the two fingers at the same time. So presumably I want the minimum of the distance between these two. That's what my D will cover. Somehow there's a cost for moving my fingers from where they were to where they are. This function will give me that cost. What is this minimum taken over? Okay.
1 to n.
Well, 1 to n, you're 1 to n. N is the length of my phone number. 12 is the number of my keys. What should this be taken over? I claim the variables that I have that are free here are what? They are L and R, right? And so I think I want L and R to be between 1 and 12, namely one of the keys that it had. L and R had to be on other keys. And I want to add one more test to it. And I want to claim either my phone number, let's say my phone number was P sub I equals F1, or P sub I equals F2. Okay, let's look at this recurrence and see what this is saying, okay? My claim is the optimal way to dial the first I digits, where my fingers end up on keys 3 and 7, is going to be, I will have had to have dialed the first I-1 digits, and my fingers have to have been someplace. Okay, let's say that the fingers were at L and R. Then, if they were at L and R, the cost was the cost of dialing the first I digits plus the cost of moving my fingers from L and R to F1 and F2 while successfully dialing the number. L and R are the the choices of what the the possible positions are, and there's 12 by 12 or 144 of them. And somehow I have to make sure that I dial actually the ith digit of the phone number, right? So for this to make sense, I want either F1 or F2 to be, where the, the ith digit is. Okay? Any questions about it? Otherwise, if, you know, for all the ones where C sub F1, F2, I, where phone of I is not equal to either F1 or F2, I probably want that to be infinite. It's pretty clear the cheapest way to do it, if I'm going to end up doing the cheapest way to put my fingers down and dial the thing, obviously at least one of my fingers has to be on the target key. Okay, I don't know if it's the left hand, I don't know if it's the right hand. Okay, but otherwise maybe I don't want to consider such a thing. Any questions about that? Do people kind of see where this is coming from? The indices, I can see you may have some trouble with, but do you see what and you know, and there's different ways maybe we could formulate this. But to see that the basic question is, to dial the first I digits, I need to know what the cost of was to dial the first I minus 1 digits with my fingers in all different positions. And the cost was then going to be the cost of getting to a state plus the cost of the change of that state, which is measured in terms of distance, okay? And, you know, enforcing that along the way I type the actual number. Any questions about that? Getting the indices right here and stuff like that, you might see, it's fair to see as messy. But does everybody see that the basic flow of the dynamic programming thing should be pretty easy? It's the cost of getting to a state plus the cost of the incremental change with conditions to make sure I only do it, well, you know, I accomplish what I need to do. Any questions? Okay, what is this distance D1, D2? So here, what do I want this to be? I've been a little bit sloppy about exactly what the cost of this thing is. If I am moving my fingers in parallel, let's think about it. Suppose, let's say I am moving my fingers in parallel. And I've got this is going to go to here. And this is going to go to here. So this was my left, this was my right. What should the cost be of the time taken to move my fingers from here like that? This is supposed to be the cost of the movement, the distance movement. If I can move both fingers at the same time, and the time is proportional to the length, maybe what I want D L F1 R F2 to be, I think I want that to be the max of the distance from L to F1, comma, distance of R to F2. Does everybody kind of see that if I'm moving two fingers at the same time, it's the longer of the two is what governs the time. So here I'm abstracting what the model of finger movement is to this function D. But basically here, if I'm defining it as being the maximum of the two finger movements, then I think that kind of makes sense. Assuming I move my fingers at the same speed, okay, then the longer of the two is what governs it. Any questions about that? Okay. Any questions about this problem?
So we're trying to move like both of our fingers to the same destination I?
Can we move okay, so I here, remember, is not a station. What is I? That's why I insist on writing out my function. What is I? the cheapest way to dial the first I digits, right? I is the index into the phone number. Here I've got a phone number that I'm dialing. And I is going to be, if I want to dial the first I digits of my phone number, okay, where my fingers at the end of it, I've dialed the first I phone digits and my fingers are on F1 and F2. What is the cost of it? I am going to claim that it is going to be, what you call it? The cost of dialing the first I minus 1 digits, where my fingers end up in a particular place, plus the cost of moving the fingers so I can dial the last digit. Okay? Any questions about that? You're saying, what is the act of the actual dialing? Okay? Remember, when I do my dynamic programming things, I am computing the cost. I am not actually saving. Okay, when I give my recurrence relation, I am giving the recurrence relation to make the right decisions. Okay? Now, when am I actually dialing the digit? Well, this part of the logic, okay, is supposed to enforce that one of my two fingers, either the left one or the right one, is ending up on the key corresponding to the ith digit of the phone number, right? So which finger is going to be the one that is hitting it, okay? It's going to be, once I have found the min is going to be for a particular value of L and R. Either L or R is going to be the one that hits the key. And I can store in my dynamic programming table, this is the cost, but I could also store what was the operation that realized it. The operation that realized it was the movement of the question of where did I move my two fingers? Okay? And so I need to store the L and the R, that one, in my dynamic programming table if I want to actually reconstruct the sequence of what were the moves that I was making. Any questions about that? Okay, can I explain this thing again? Okay, now my goal here is understand that I want to dial a phone number. My phone number here is given in an array P, where if I want to dial, okay, I'll give you my office number, okay? Okay, if I'm going to dial that phone number, the ith value, okay, yuck, sorry. For a given value of I want to find what is the cheapest way to dial the first I digits where my fingers end up on the keys, 9 on the left and 3 on the right. Let's say that that's what I wanted to know. This was F1, F2. Now, if I'm getting the cheapest way to dial this number, my finger had better end, one of my fingers had better end up on the ith digit of the phone number. Does everybody agree that the cheapest way for me to dial this digit, the phone number, at the end, I'm going to push the button when the button for the last digit, and I'm going to stop. So this is now telling me, okay, this is sort of logic to enforce that I actually type out the keys of the phone number, okay? And either the left finger or the right finger is going to be typing the digit. But if it's the right finger that's typing the digit, I might still want to move my second finger into a position where it's ready for the next thing to type. That's what the dynamic programming is going to try to figure out. Any questions about this? Okay. The important thing is to not that there's some level of details that may look messy, but the structure of the recurrence should be relatively clear. Okay. Now, last question: what is the running time of this this recurrence? Anyone want to tell me? Well, let's say that I've got n digits for phone number. And let's say I've got a K keys on my keys on the phone. So n is the number of digit length of the phone number I want to type out. Pop, 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 pop. And I've got K keys on my thing. What is the running time of this algorithm for dynamic programming? How do we go about what you call it? How do we go about computing the running time? What is the running time? Does anyone remember? How do you compute the running time?
Number of box times time per box.
Number of boxes times the time per box. How many boxes do I have here? As a function of n and k. Typically, it's the product of the number of possibilities for everything. How many choices are there for where finger 1 can go? How many places can finger 1 go? Somebody. Okay, if we have n K keys on the phone and n digits in the phone number, how many places can finger 1 be, possibly be? Now I'm seeing K. There are K choices for finger 1. There are K choices for finger 2. There are how many choices for the last one? For this thing, the index into the phone number, how many choices there? N. Does everybody see that there are n times k squared boxes? Now, how much time does it take to fill a box?
Wait, Professor, could you explain again why it's n times k squared?
Okay, the dynamic programming table typically will be a matrix. In this case, it's a three-dimensional matrix because I've got 3 arguments, where the first one specifies what key is my left finger on. The second one specifies what key is my second finger on. The third one specifies how far am I in the phone number so far, right?
Yes.
On my phone, there are K places I can put my first finger. There are K places I can put my second finger. And there are n digits that I ultimately have to type in the thing. I'm going to end up with a K by n matrix.
Got it.
Okay.
Thank you.
Now, how much time does it take to fill one cell of this matrix? Okay. How much time? What am I going to do? For each value of the arguments, I am going to look up something in a table. I am going to compute a distance function on 4 numbers. How much time will it take to look something up in a table? 1 step. How much time will it take to compute a distance between 4 numbers? 1. 1 plus 1 is 1. Now, how many times am I going to be computing this? Well, it's 1 times all the possible arguments I need to evaluate for the min. L is going to be between 1 and k. and R is going to be between 1 and K. Does everybody see that? I claim it's going to be K squared time per box times N times K squared boxes. As the way I have done it, my total running time is going to be N times K to the 4th. Now, K on my example here was 12, so that might work out to be a constant, but I think it's more instructive to work it out as a function of K. Maybe I've got a big telephone, maybe there's countries that walk around with telephones the size of an iPad, and they have hundreds of keys on them. Okay? Any questions? Okay, I'm hearing some question, but I can't understand it. Does someone want to ask it? Any questions about how this works? Going once, twice. Okay, Sol, anyone who wants to ask something, use their voice at the count of 3, or I'm going to next something else. 1, 2, okay, why is it K squared boxes? You're saying because, okay, so there's a question here about why am I using all K squared choice time? Because one of the fingers is staying in the same place. Now, that's an interesting question. First of all, it's not clear that the fingers are staying in the same place, because if I'm smart, while I'm moving one finger to the other goal, I would also move, one of my fingers to the other goal. Okay. So if I know that I'm going to be typing 92, 92, 92, when I move my fingers first, I'd be better off putting 1 on 9 and 1 and 2 looking ahead. And that's what the dynamic programming essentially can do. Now, there may be a following question of, am I overestimating things? Because I'm counting the number, all possible values of this argument by all possible values of that argument. That certainly gives me an upper bound. That's certainly good for a big O thing. Now, maybe what you're noticing, somebody, is that since one of these fingers has to be basically, well, actually, no. This says that the short answer is no. I think I like the idea that it's K squared. I'm doing one of these fingers has to be where the ith number is. But L and R could both be different numbers, and I'm moving them to some place that's going to be from some place that's kind of helpful. So I am going to hold to my my analysis here. Any questions about that? You're saying, how can I look at dynamic programming, look ahead to fill out the ith plus first position because we didn't do it? What is looking ahead in back? Recognize that, okay, so this is an important thing. In dynamic programming, think about a recurrence. In a recurrence relation, how do recurrence relations work? You start at the big values and you break it down into smaller cases. Does everybody agree that's what a recurrence relation does? To solve this big value for the I, it looks at smaller values. Does everybody see that? But when we are filling in, but in dynamic programming, instead of starting from the biggest value and calling things recursively to smaller things, we're filling the table in, okay, for all possibilities of small things until we get to the point that we have everything we need to compute the big thing. Computing the small things when you're evaluating it to fill the table, okay, it is providing the stuff so when you fill out the last value, You're looking at all the possibilities. When I say looking ahead, recognize that I am trying to build up potentials, the best way to solve small problems, because that will tell me the best way to solve the bigger problem. Okay? And when I am implementing, again, in a recurrence relation, I start with my big call and I evaluate smaller things and keep going down till I get to a base case. In dynamic programming, I will fill in my table from the smallest parts to the biggest parts, okay? Because I want the numbers that I need. I don't want to make recursive calls. I want to look up the values that I need in constant time. In order to solve it for the first I digits, I need to know how to do it for the first I minus 1 digits. Let me start out. What's a basis case? What about where I dial 0 digits? Once I know what that is as my basis case, I can figure out the cheapest way to dial the first digit for all finger possibilities. Then the cheapest way to dial the second digit for all finger possibilities. ... and work up there. Any questions about that?
If we can't move both fingers at once, would a greedy algorithm work for this?
If you can't move two fingers at once, then perhaps, certainly if you have one finger, there's no decision. Okay, if you're moving two fingers, you can't move them at once. I'm still not sure I would believe the greedy algorithm. You need a proof for this. Because I think that it might still be the case that, let's say I have two fingers that are equally likely to be, what you call it. I have two fingers that are equally distant to the prize. I could either move this or this. The right choice depends upon what the next digit is going to be. So I'm going to want to know what's the best solution, where I move this to the prize or where I move that to the prize. So that for the next value, for I plus 1, okay, I can make the best of the possibilities, okay? Depending upon what you're doing, maybe greedy will work, but you need a proof. I don't really need a proof because I'm doing exhaustive search. I am trying every possible previous configuration. And I am scoring it by the cost to get there plus the cost of the incremental change. I have to be right, okay? You have to make some kind of a proof that your greedy algorithm works, okay? You see why I like dynamic programming? I'm doing exhaustive search, so I'm going to know it's correct, okay?
Okay.
Any questions about that? Any other questions about this problem? Going once, going twice, sold. Okay, what I'd like to now do, I could go on to a lecture material. I've got about 20 minutes, and I could do it, and I will do it if I don't get a good question. But is there a dynamic programming problem, perhaps from the textbook, perhaps from a homework, that someone would like to see me do? Preferably someone with a voice.
8-14 is proven difficult for me to get started on.
8-14. What is 8-14? I'm now going to look at this here book.
It's the one with chess and the different probabilities of winning. We're playing white.
Oh, okay. So this is this one about a chess championship. Okay. So we have a world where in chess, okay, when what's his name? Magnus Carlsen. Magnus Carlsen, I think he, is going to play a chess championship. In chess, what happens? They play matches of 24 games, typically. I think, did I say that it was 24 in there? Let's say you play a total of n games, and you win whenever you play a game, you get a win. For a win in chess, you get 1 point. For a loss, you get 0 points. For a tie, you get 1/2 points. A draw, you get 1/2 points. Now, suppose we and the way that chess matches work in this thing is they alternate between whether the champion is going to be playing white or black. I think actually I guess the champion usually starts on as I understand it, black. Let's say that that's true. White, black, white, black, white, black, white, black, white, black, white. Okay. Now the advantage in chess is that you get to play. If you're white, you have an advantage if you're a good enough player, because you get to set the opening. Okay. And the question really is, if we know the probability, the claim here is that there is a different probability for winning, drawing, or winning, drawing, or losing, depending upon whether you're playing white. So suppose we have a particular chess champion. We know the probability of him winning, drawing, and losing when he is white and when he is black. Now we want to find what is our function, what is the probability that what would be a recurrence relation that would help us know what is the goal here? We wanted to figure out what's the probability that somebody is going to win. Okay. What would be a recurrence relation that would help me know whether it's win? And I'm going to set the following recurrence relation. What if I have the probability that after I games, I've got P points? What is the probability that the champ has I P points after I games? Does everybody believe that this is a useful thing that will to help me try to figure out whether the champ is good, what the probability is that the champ's going to win? Right? What would be the probability that the champ could accumulate 12 points after his first 12 matches? It would mean that he had to win here, here, he or she had to win here, 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 the first 12 matches. It'd be the probability of winning on black times the probability of winning on white, black, white, black, white. Does everybody see that? Now, is there a recurrence relation that you can give me? Again, I defined my function in English. Now, can you give me a recurrence relation to tell me what is the probability that I'm going to have P points after my ith game? Let's first forget about whether the games are white or black. Can anybody give me a recurrence relation for this?
Probability of like winning I-1 games with P-1 points.
Okay, it should be a function of what my chances are that after I-1 points, I had P points.
Mm-hmm.
Is it anything else that it's a function of? Let's think.
We can get like half points. Maybe you can include that.
Okay. I am going to claim that it's going to be, there's a couple of different possibilities. If I'm going to end up with P points, I claim that there's going to be 3 probabilities I'm going to care about. This is going to be either on the Peth game, either I'm going to win, I'm going to lose, or I'm going to draw. Does everybody agree? If I am going to end up after I games with P points, I claim my probability for doing that is what? It is going to be the probability, the win probability. Right? If I win, that's W be the win probability, D be the draw probability, and L be the loss probability. Does everybody see that this formula is pretty much what I want? The probability of me ending up after I games with P points is the probability I had I P points after my I minus first game and I lost, plus the probability I had P minus 1/2 points and I drew, plus the probability I had P minus 1 points and I won. Does everybody kind of see that? This is now a recursive function. This value is depending on the previous values. And these loss, draw, and wins are going to depend upon the right value of L, D, and W. Will depend upon whether the games are even or odd, whether I'm white or black. Does everybody see that it's an equation like this? That is a recursive function that is going to tell me what the probabilities are. Okay? Any questions? Okay.
Do you stay playing white if you win, though?
What?
Do you stay as playing white if you win the previous game?
No, in just you alternate. Black, white, black, white, black, white.
Oh, great. Well, that would have made this a lot easier from the start.
Okay, sorry about that. Okay. Follow
No, it's
follow
my
the
fault.
chess championships. Okay, any questions?
I did have one question. Where are you accounting for the black and white in the recurrence function that you have?
Okay, where am I doing it? Right now, I am kind of concealing it by saying if I have these win probabilities, loss probabilities, and draw probabilities. Does everybody agree that right now I just have them being described by these values L, D, and R, right? What if I made it L of I? Sorry about this. Uh-oh, I'm in trouble. D of I and W of I. What is the probability of winning of L sub I? What is the probability of me losing on my ith term? I want to play if I am white on, okay, if I is odd, okay, let's think about it. 1, 3, 5. When it's an odd number, does everybody agree that it's black? So the probability of me losing on black on the ith term is going to be, B of L. If, okay, if I is odd and W sub L if I is even. Does everybody see that that's really what's going on here? Okay, I'm going to define a separate function that's going to return the right loss probability as a function of I. And that's doing what I want it to do. Does that make sense? And I'm going to do the same thing for D of I and W of I.
So I understand what you're saying, where depending on whether you're playing as black or white determines like the like the value of Li, Wi, and Di, but does the function also depend on the value of I? So like, does
Yeah,
your,
it depends on I. That's why I'm going to do my function L sub I is going to return this if I is odd, and this if I is even.
okay, so like W10 would be different than W5. Like,
W10 is different than W5, but W10 is the same as W8.
oh, okay, that's what I was asking. Sorry, is W, so as long as it's even, but the values are different, they would be the same. W of any even value would be the same.
Exactly right.
Okay.
Exactly right. That's because they happen to play, they alternate black and white.
Got
And
it.
if
Thank
there
you.
was some other complicated rule, like let's say Magnus got to be white when I was prime, you could encode it in that. And then the dynamic programming would figure it out what the right thing to do is.
Got it. Thank you.
Okay, any questions about that? Okay, do people see? Again, the key thinking here is I have to construct a function, which I describe in English, that tells me what I want to do. And then I figure out how to express it in terms of values with smaller indices. That way it's a recurrence that's making progress. Any questions about that? And then I've got to deal with this, on some level. What is the probability? What is the basis case here going to be? Does anyone want to give me an idea of a possible basis case that would be interesting? What is the probability that I have 0 points after 0 games? Does anyone have an idea for what that should be?
1.
1. If I went in against the world champion, I can guarantee you I'd still have a probability of 1, okay, of having 0 games, of being tied with them up until the moment the match started. Okay, that's the basis case. Any questions about that? As ways of thinking through these things. Okay, there's kind of a reasoning here that you have to do. There's a certain amount of details in getting the indices right that maybe I'm being a little cavalier about, but I want you to understand. And what's the running time here? How many boxes are there if the match goes n points long? What are the possible values of my first argument here?
N games.
What?
0
N.
for N games.
And what's the value of P that I'm going to be interested in? How many points?
2N, because it goes by half points.
Okay, if it could be that I have, okay, that's a reasonable upper bound. P's here, in fact, are going to include half points. So you're right. I guess I could have 2n possible totals of what that would be. That would mean that it's going to be n by 2n, which means I've got n squared boxes times how many points per box? How much time per box? Look this thing up, multiply it by a constant, plus look this up by multiply, look it up, 1. This would be an order n squared algorithm. N squared boxes times 1 time per box. Any questions about that?
Thank you. I feel quite relieved now that I know the games alternate.
Okay, well, okay, sorry. Okay, good. Okay. Any questions about that? Okay. And if it didn't alternate, but there was something funny going on, okay, whatever rule you could come up with for how the game should proceed, okay, you can encode that here. The way you would make that encoding is by changing these L sub I, D sub I, and W sub I functions to reflect what the probability is of winning each individual game. Okay? Any questions?
Professor, can I ask a different question?
What?
It's the one about arranging books on a shelf where the like heights of the books is like not constant. It's
Oh.
819 on the book.
Page 819, and this will be the last one I'm going to do because I saw some people were fetching that I run too long these days because we're on the television. But what does this say? This says I am trying to store books, okay, and each book has a thickness and a height, and I want to try to minimize the height of the total bookshelf. So let's just make sure we're understanding what the problem is. I want to build a custom bookshelf to hold all my books. They have to appear in the same order, but I want to minimize the height. Now, it should be clear that if I'm finding a bookshelf that is going to, be the one of minimum height to hold all my books, it should be clear that on every shelf, one of the books, the tallest of the books, has to be of a height equal to the gap, or else I could make my bookshelf smaller. Does everybody kind of see that? Let's say here's another one. Let's say that I had a book here, book here, book here, book here, book, book. This is probably not the optimum way to do it. I would probably have been better off taking this book and moving it to that shelf. That would have lifted this up. And then the last shelf here, that would have given me a solution that would probably be shorter. That would give me a solution that would probably look something like this. The last shelf is going to be that. The shelf above it is going to now be this book, followed by this. So the question is really, what is the minimum height? So what am I going to say? I am going to say, let's let, I want a recurrence relation that might help me. Let's think what I might want. I usually think I want to know let's see if this is good enough. C sub I is going to be the shortest height shelving of books B1 to BI. Okay? Let's say that that's what I wanted to do. This looks like it could be a helpful thing, right? What is, can anyone give me an idea for a recurrence relation to compute what that would be? What is the cheapest way to file the first bookcase, to put the first I books down? Can anybody think of what that could be?
Wait, Professor, how can you move the books around the way that you're doing it if in the question it says that the ordering is fixed by a cataloging
The
system?
ordering is fixed. I can't take this book here and move it up to the top. But notice that this book is the first book of this shelf, and there's a hole at the end of this shelf.
I see. Okay.
You
Got
see,
it.
that's the decision I have. If I've got a book, might I want to take a tall book and move it down?
Got it.
Right? So what is C sub I? What's the cheapest way to put this down? To put down the first I books? Can anybody think of a recurrence relation for this? I claim, what am I going to want to do? First of all, what is the first book on my last shelf going to be? We agree that in this thing, book I is going to be on the last shelf. What is what is the first book that's going to be on the first shelf, the last shelf? Can anyone tell me what book that is? I'm going to tell you that's book J plus 1. What is the cost of my solution if the first book is going to be at position J minus 1 on the bottom shelf? Does anyone have an idea? I think it is going to be the height. The best possible way to file the first J books plus what? I am going to claim that it's going to be the max of the height h sub k as k goes from J to I. Let's think about it. What is the height of the last shelf going to be? If it has books J plus 1 through I, what's the height of the last shelf going to be? Is it going to be the tallest of the books?
Yes.
Yes. This is going to be the height of the tallest of the books, right? This is the cost height of filing the first J books here. Now, what is the value of J that I want it to be? I am going to claim that the best J is going to be what? It is going to be the minimum over all J of this sum there such that the width as k goes from J to I, the width of k is less than the max width. Okay, let's think what this is saying here. You know, my handwriting is bad. Can I pick any possible value of J for the number of books on the last shelf? As I recall, this problem limits the width of my shelf, right? If I wanted to minimize the height of the total height of my bookshelf, how should I do that? Does everybody agree that if I didn't have a width constraint, I just line the books up on my floor and my shelf there'd be only one tier. If I am fixing a maximum width of my shelf, however, there is only a certain number, and I know it's going to end on book I. Well, my value of J is going to be any J such that the width of the books from J to I is less than my maximum allowed width. That is what I am doing here. Okay? So for all legal choices of J, so that my last shelf has room, okay, I want to minimize the cost of doing the first J, all the shelves above it, minimize the cost of all the shelving above it, plus the cost of the highest book on the last shelf. And that's what this is. Any questions about that? Can anybody come up with any basis case? Any basis case? What is C of 0? If I wanted the shortest bookcase when I have no books on it, what would that height be? I claim 0. Okay, any questions about it? What is the running time of this algorithm? How do we compute the running time? What is our magic formula for that? Number of boxes times the cost per box. Assuming we have n books, how many boxes do I have here? How many boxes in this recurrence? Anybody there? Okay, I've got n boxes. How much time per box? I'm gonna have J is my index of my main min. Okay. If I did that, what am I gonna do? J here is gonna go at worst from 1 to n. Right? I could go back any number of books here. Looking something up in a table is that. Finding the maximum value in the range from I to J. If I did this in a brute force thing, this would be another factor of n. Does everybody see that? If I didn't do any pre-computing or anything smart, if I have to find the biggest height of the books between J and I could be as big as n. Finding the maximum of that is going to be, If I did it in the dumbest way, this would be n, this would be 1. This would tell me that the cost of filling this is 1 plus n, meaning n, and it's going around n squared time. If I did this in the dumbest way to do it, it would be n squared time per box. But if I claim I can compute what the if I could find a faster way to compute what was the biggest the biggest book from I to J, the tallest book from I to J. If I could answer that query in constant time, then this would be n time per box. Okay, so done in the dumbest way, this would be order n cubed. But I believe I could come up with a data structure to do this computation faster. Any questions? What is on top of the CI? What are you concerned about? You concerned about this? Okay. What does the CI on top say? CI is the shortest height shelving of books B1 through BI. That's what this is saying. Any questions? Okay, look at these, try the homework, read the book, do the best you can. Don't make yourself crazy, okay? And good luck, and we'll see you at the exam on at 3 o'clock sharp, okay? Actually, so I need you guys to log in to the browser. I will be logging onto this window in case somebody got into trouble. But I am hoping you guys are not, okay? I'm hoping you guys are diligently sitting on your HonorLock browser and getting the scores and answering the exam and feeling good, okay? Good luck. Take care. And this is where I'm going to end it.